So in this video, we are going to look at deep convolutional neural network to solve the problem of recognize images which are available in CIFAR10 dataset. So the objectives of this video are specified here. We will review MNIST performance using CNNs that we discussed in the previous video, and then understand a CIFAR10 dataset, and then apply whatever we applied for MNIST on CIFAR10 dataset and see how the results are. So we try to see if we can improve the accuracies using by increasing the depth of the convolutional neural networks. By adding more layers, can we improve the accuracy? Further accuracy improvement is done through data augmentation, which is by using generating additional images from existing images by transforming them slightly and then feeding into the as if it was the actual input data. So we will also look at where the model is not able to learn properly, and finally have some discussions about what else can be done and why what are the limitations of this deep convolutional neural network. So what you see in this image is a CIFAR10 dataset images, some examples of it. The description of this CIFAR10 dataset is shown here, and then it's essentially about images of 10 classes which are specified here: airplane data, automobile data, bird, cat, and so on. And our task is to recognize, given an image, we're trying to say, okay, this is an airplane. If you're given this one, we have to say it's a bird, and so on. So there are 50,000 data sets for training, and then about 10,000 for testing. But before that, let's look at what we review what we did in the past and continue from there. So this is my setup where I have a NN Keras folder, and within that I have data, notebooks, and images folder. So this is where my scripts are, and this is where my images are, and this is where I store my data. So in the past, we looked at MNIST dataset with convolutional neural network, where we try to recognize these handwritten digits. These images were 28 by 28 images, and we used convolutional neural network to recognize it. So the code that we used in the past is shown here. So this is a functional API. If you are used to writing sequential code, this is slightly different, but if you look at my previous video, you'll understand that why this is more convenient. These functional APIs are more convenient when the models are more complicated. Like, for example, you have 2 inputs or 2 outputs from a model, then having a functional API is a lot more convenient. So what we did for MNIST dataset is, the first thing is to reshape. We were given a 28 by 28 image data that we are adding additional dimension to represent a channel, and then we rescaled it to normalize pixel values, and then we applied a convolutional layer with 32 filters, and again 32 convolutional layer with 64 filters, with kernel size as 3 and padding same, and activation function prelude. So we used a maximum pooling, we used a dropout and a dense layer, and finally an activation function softmax for the output layer. So the functional layer definition, 2 things are important. One is the input layer, and the other one is the output layer. So we define the outputs here after all of these transformations, and the input is the input shape of the image that we transformed before transformation. So the model is defined in this format. So we say model input is equal to inputs, output is equal to outputs, and we can name it whatever the model we want to name it as. So finally, the compile will specify the last function, which is categorical cross entropy, and the optimizer, we can choose RMS prop, SGD, but we have chosen Atom, and the metrics is accuracy, which is what is printed when you are fitting the model and running through epochs. This is the metric that we see. and history, this is where we are fitting the model fit, and the results, accuracy and loss and everything is stored in this particular variable while it's running through learning process. So the number of each batch is holds 512 example records, and we are running this whole model 15 times through the network. So all of the training examples are passing through the network about 15 times, right? And each time we are passing about 512, and then we will pass so on until one epoch is done, which is about 60,000 records that we are passing, and then we'll continue to do that 15 times. So finally we evaluated the model and printed the accuracy. Okay, so we saw that the accuracy was for that particular model was 99.2%, which is pretty decent, given that multi-layer perceptron model gave about 98% and this one gave 99.2% without doing a lot. We just added 2 convolutional layer and with the max pool layer in between, and we got 99.2%, which is pretty good. So let's see what happens if we apply the same model for CIFAR10. So I coded the CIFAR10. The Y data is provided in the numerical format, so I coded them in this way so that it's easier to understand when we are trying to plot the maps. So it's an image dictionary. So these are the images that we loaded. These are the training data set, and as you can see, the dimensions of the images are 32 by 32 by 3. This 3 represents our RGB channels, red, green and blue channels, and there are 32 by 32 size images. So we are running through the same model. There is no difference except for the reshape. We don't have to reshape because the input shape already has the channel information in it. In the past we tried to add +1, but here we are already given RGB as a channel, so we already have 3 as the input, so we don't need to change. So the inputs are same and everything else is pretty much the same. So let's see how we get what is the accuracy. So the only difference I can say is that we are running 100 epochs and we are trying to look at the accuracy. As you can see, we started running 100 epochs, but after about like 40 epochs or so, the change is very minimal. I think it remained about 73%, and finally on the test data set you see 73.4%. So from 40 to 60 iterations, it didn't really show any improvement. So what can be done to show improvement? So one thing that we can think of is, can we add more layers to get more convolutional layers to get more improvement? So that's how we build a deep neural network model. So this particular model is inspired by VGG. So what VGG 16 network has is, it uses 2 convolutional layer followed by pooling, 2 convolutional layer followed by pooling, and 3 followed by pooling, 3 followed by pooling, and each layer it increases the number of filters. So which is the inspiration we take. We are only going to do 3 blocks. Each of these is called a block, and we are going to build a network with 3 blocks, which will contain essentially 2 in each block convolutions, so about 6 convolutions, and then finally we have 2 dense layers. So let's look at how we construct it. So in the first block we are going to have 32 filters. We do the pooling, and in the second block we'll have 64 filters. We do the pooling. Third block will have 128 filters. We do the pooling. So that's essentially what we wrote here. So we are saying 32 times 2 per blocks, and the blocks we are iterating to the number of blocks. So there are 3 blocks, 0, 1, 2. So here 2 power 0 is 1, so there are 32 filters. So we are passing 32 filters in both of these convolution layers. Everything is same. I think this is this is a change. Again, in the VGT paper they used this particular initializer, so we are using the same initializer, but the default initializer would work as well. So one change that you will see is batch normalization. So we all know what normalization is. Essentially we are standardizing the input data, for example here, by dividing by 255. We can also normalize by subtracting the mean and dividing by the standard deviation. So that's a normalization. But what is a batch normalization and why is it done? So the reason why we are scaling our input data is to give the network is kind of like a stable data. If their outputs, they are shrunk down to within certain range, so the models are better at learning those. So what batch normalization is, the output layer after passing through activation layer, it will generate the z values, which could again since we are going through so many layers, after certain layers it is possible that those output values become outliers, like something like an outlier. All of the way z values are smaller, but maybe let's say 2 or 3 values are really high, so that will cause problems. So for the later layers, and the convergence becomes a little bit difficult. So batch normalization helps to standardize the outputs. That way the convergence becomes easier. The outputs from each of the layers becomes stable. So it definitely helps in making these deeper models work better. So that's one additional change to introduce batch normalization. And then we are doing 6 convolutions because 3 times 2 convolutions. And then after that we are running a deep network with 128 layers, and then finally running output layer with softmax activation. So again, there is no change in terms of how we are running the model. This is the functional model, so we are declaring a functional model, and then we're compiling it, and then finally we are fitting the model here as shown here. So again we are running 100 epochs, and because it takes a long time, you can save the model as shown here. So let's look at the accuracy here. So it started very poorly with 0.1433 accuracy, but as the time went on, I think the accuracy became decent around epoch like 24 or so. But here again it oscillates a lot, like it goes 80, it goes to 81, and then sometimes it goes back to 80, 83. We see 83 at 35, and then it stays there, but it is more or less staying there. Yeah, 84, again it went back, 82, 84, so on. Yeah, so it went back to 80. Maybe the learning rate needs to be adjusted a little bit, because it's kind of oscillating between, it's going down and going up between 83 and 80. So that's something to be noted from here. So essentially in the end, the accuracy is about 83.5%, which is pretty decent. We went from 73 to 83. 10% improvement is decent, but you can see the time it takes is 5,000 seconds, which is close to 2 hours. So how can we improve it further? So one thing that we can definitely try is improve the number of layers, but we can discuss from, like right now, 3 blocks. Instead of 3 blocks we can have 6 blocks or 10 blocks, but we can discuss about what happens if we increase the number of blocks. In fact, what is observed was that as the number of blocks increase, the training accuracy stops improving. After some time it becomes even worse. It's not about overfitting, but it's more about it's not able to learn anything more, because the number of parameters increase, and there is also gradient explosion or vanishing gradients. Those problems occur as the number of layers increase. So for the number of layers we have, it is doing a decent job. We can definitely try, instead of 3 blocks, maybe 4 blocks or 5 blocks, and test it out. That's one change. The other change that we can try to do is what happens if we try to augment our image data. So what is this image augmentation? Let's look at one example and come back to running CNN model. So there is this particular class within Keras. This is called image data generator, and within which we can give various options to transform images and generate new images. So we are saying rotate my image by, you can, between 0 to 40 degrees. You can shift by 20%, width shift by 20%, height shift. You can move the image down by 20% or up by 20%. You can shear, you can zoom range is 0.2%. Horizontal flip, you can change the direction of the orientation of the image. And fill mode is the nearest, whatever if it is moved, for example, the image, whatever is the last pixel, the same pixel is reproduced in the empty space. So this is image data generator, and you can use data generator flow, and then if you pass an image, for example, it will modify this image based on these inputs. It will generate many images. It will generate one image with rotation range, one image with shifted width shift, one image with height shift, and so on randomly. So let's look at one example here, and we can understand what happens. So the image is car image, that is the input, and we are the outputs about 10. We are moving into augmented data. So let's look at the car image. So this is the input image. This is what the image was given, and then when we run the image data generator, so it will produce various kinds of images. For example, this image, this is the horizontal flip of the image, right? So it also did some shearing here, left shear. You can see this car moved far towards the right. Let's see this. Yeah, this one went out of the scope of the image picture. What else? Yeah, this is going in a different direction as we have seen before. So it definitely generated different kinds of so it changed the orientation, but also it sheared the image. So different kinds of images are generated, and these images are can be passed into the model. Let's look at how this can be done. So here we are trying to run the same model, so but with augmented data. So what is being done here? So the same model as we have done before, but the change happens here. We are saying use augmented data is equal to true. So here I have thing, if not, this is the what we did in the previous block, but now we are saying this image data dot generate. We are feeding the image data, and we are generating a flow of X train and Y train, and then we are giving this band. So every epoch, it's going, images are being generated by this flow rather than within X train and Y train. This class will take images from this dataset, and randomly it will transform the input data and pass it on to the model. So I increase the number of epochs to 150 to allow additional images to be passed on. I think 150 is probably not enough. Maybe 200 or 500 epochs can be done, but we can look at the results. So I ran it through this process, and you can see immediately the accuracy started improving from the first iteration itself. So it was 0.49 and then 0.6, and then it started improving. So by iteration 35, or even before, here by iteration 32, you're already seeing 86%, and finally by the end of these 150 iterations, you see accuracy to be about 88.9%, close to 89%. So, but definitely it is oscillating between 89 and 87, which means if we try to decrease the learning rate, maybe it will slowly improve rather than oscillate. So learning rate parameter can be adjusted. Again, the time taken is probably 4 hours, which is quite a lot, so it's definitely good to save the model. So one way to achieve optimal adjusting the learning rate, which is given in the paper, VGG paper, is to use this learning rate where if the number of epochs is greater than 180, you're multiplying by 10 power minus 3. If it is 80 or so, it's like 10 power 0.5 times 10 power minus 5, or 5 into 10 power minus 4. So that's where we are starting, and then as the number of epochs increase, you're decreasing the learning rate. So, and you can give it in the model.compile statement to make this effective. So those are the two changes that we can do. And after this, let's see error analysis. So error analysis is where we are trying to understand where the errors are occurring. So for example, so what I did here is like I got the predictions from based on the previous code, and I'm generating. So the predictions are more in the it's probabilities. So I'm using axis 1, and I'm saying give me the maximum index from the probabilities. Like, so it is generating a unique number for an array, and then we are taking that as a prediction, and by dx we are reshaping it so that this is actually 2-dimensional array, so we are changing it to 1-dimensional array now, so that predictions and y-test data are in the same dimension. So I'm passing it to this sklearn confusion matrix function. I'm passing test and preds. So as you can see, this is the confusion matrix, and I did plot using Seaborn, and you can see automobiles are detected very well, right? So you can, it has detected very few errors are happening. Again, the ship is also in the same way, truck is also in the same way, perhaps airplane also, it's doing a decent job, but there are some cases where it's not doing such a good job. For instance, a dog, you see that it's 128, so it's confusing dog and cat, which is understandable, and also cat is being confused to dog. So you can take a look at it, this does make sense. So you can take a look at the input data and see what can be done to improve better classifications of cats and dogs, right? So that's something that we can look at. Maybe generate more data if they are cats and dogs, something you can try different things. Okay, so for example, if I try to, I'm not going through this code, but this is the code that you can do error analysis with. So what I'm giving is, this is a dog index and this is a cat index, and I'm generating all the cases where the actual data was dog, whereas the prediction was cat. So these are all the images where the actual images were dog, whereas the model predicted it as cat. So this is how you can do error analysis, and with this one I think I'll wrap up this video. But before wrapping up, let me summarize what we did in this particular section. So we went through MNIST dataset and the convolutional neural network code from last time, and then we applied the same code on the CIFAR10 data, and we saw that the accuracy was 73%. And then finally we tried to improve the model by adding more layers, and then we looked at VGG, which is inspired by VGG, and we saw that the accuracy was about 83%. Finally, we tried to augment additional data by adding more images, by transforming the images slightly and adding to existing images, and we saw that the accuracy improved to 89%, but the number of epochs were, I think, insufficient. If it probably run it more longer, maybe it will give accuracy beyond 90%. So what we didn't discuss, and probably we will discuss in the next video, is what happens if we try to increase the number of layers. Here we use 3 blocks. What happens if I use 10 blocks, which means about 20 layers or further? So what will happen is that after certain number of layers, the number of parameters actually grow quite significantly. And then also you'll start noticing gradient explosion or gradient vanishing problem starts occurring, and you don't actually learn anything. The parameters are not changing much after certain layers, so there is not a lot of improvement after certain number of blocks. So how do you solve that problem? Microsoft researchers wrote one paper known as ResNet,